In today's presentation, I want to talk about two additional topics related to redox reactions. And these are going to be what we call electrolysis and corrosion. So first of all, electrolysis is sort of the opposite of what we think about when we think about a battery or a voltaic cell. So while voltaic cells were utilizing a spontaneous redox reaction to generate electricity, an electrolysis cell, electrical current is added, right, to drive or to force, if you will, a non-spontaneous redox reaction to occur. So basically, we're going to force something that wouldn't be spontaneous to occur by supplying electrical current to it. So one way to think about this is we're going to use a voltaic cell, or potentially we use some sort of voltaic cell, we could, to drive or to force an electrolysis reaction to occur. Now, the cells that we use here are called electrolytic cells. So there's two types of electrochemical cells, right? We talked about voltaic cells, and now we can talk about electrolytic cells, where electrolysis takes place. Now, we're not going to go into quite as much detail with electrolysis as we did with voltaic cells, but we're going to hit some of the big pictures. So what are some of the applications of electrolysis? Well, we know that hydrogen and oxygen can come together to make water in a fuel cell, right? So this is a classic fuel cell here. But we can also take water and break it down into its elements by adding electricity, right? It consumes electrical current, and that occurs in an electrolytic cell, right? So one application of electrolysis is to break down compounds into their elements. Now, I talked about fuel cells, one of the issues being supply of fuel, right? Supply of specifically hydrogen. Well, one application, one potential source of hydrogen that's been looked at is actually water, more specifically the electrolysis of water. So you could, in tandem, have a fuel cell, right, powered, connected, or with an electrolytic cell that would be hooked up to some source of electricity. Maybe it's solar panels on a car, or maybe it's other batteries, right? Some source of electric current that can drive the hydrolysis or the electrolysis and create hydrogen that can then be used by the fuel cell. And then that would convert it back to water, and potentially the water that's produced in the fuel cell could then be recycled back into the electrolytic cell. And so we could have this nice sort of setup where we have electrolysis that's creating the fuel used in our voltaic fuel cell here. Now, I just showed the electrolysis of water. I'm just going to show a picture here. And so the idea is we're going to hook up to some source of electric current, like a battery. And we're going to run that electric current through our electrolytic cell, right? In this case, our solution of water here, our water. Now, on one side here, we're going to have the formation of oxygen. On the other side, we're going to have the formation of hydrogen. Right? And so, if we look back at that reaction, right, we have the reactions going on is we have +1, -2, right? And so, hydrogen is going from +1 to 0. Oxygen is going from -2 to 0, right? So what's happening at each one? So the hydrogen is gaining that electron, right? Going from +1 to 0. So it's undergoing reduction. The oxygen is losing those electrons, undergoing oxidation. So we're going to form oxygen gas at the anode. We're going to form hydrogen gas at the cathode. So the oxygen gas is forming here. The hydrogen gas is forming here. Now, if we think about why is there a bigger area here? Well, think about water, right? If we have water going to hydrogen plus oxygen, if I were to balance this equation, I'm going to have 2 and goes to 2 hydrogens and 1 oxygen there, because in our compound we have twice as much hydrogen as we do oxygen, so it makes sense that we're going to form twice as much hydrogen gas as we would oxygen gas. So again, reduction here, oxidation here. So what about some other applications of electrolysis? Well, now remember I said that most metals prefer to undergo oxidation, right? They exist in their ion form. Well, maybe we want to take those metal ions and get them back to the metal. Well, that's not going to occur spontaneously, right? They're sitting in the Earth's crust as their metal ions. That's going to be their stable form. We're going to have to force them back to the metal. And so one of the places where we use electrolysis is to convert metal ions, right, that are found in the ores, right, in the earth, and force them, drive them back to be the pure metals, right? So to convert these metal ions back into the metals, we can use electrolysis to do that. We can also use it to what we call plate metal, or deposit metal on top of other metals, right? What we call electroplating. And this is how we plate metals, right? This is how we get gold plating and silver plating and copper plating and nickel plating, etc., right? We deposit thin layers of metal on top of other metals. And so in this kind of situation, we can look at a picture where we're going to look for silver plating. And so if we think about, we have our source, right? And at our anode, right, we have a silver electrode. At that silver, we get oxidation, right? So we have silver forming silver ions, right? Now, and then that's going to cause electrons to be released, and those electrons are going to flow to the positive terminal of the battery, right? The cathode, right? Now the anode of the battery is producing electrons, and those are forced or drawn to the cathode of the electrolytic cell, where those electrons are used to reduce these metal ions that are present in solution. In this case, silver ions, and those silver ions are converted to silver metal, which is deposited at whatever our metals that were here that we're depositing onto. And so we're forcing the oxidation of the silver, and then the reduction of the silver ions, which would not occur normally, right? If we mix silver with silver ions, there's no potential there, right? We have the same reaction going back and forth. The only way we can get this reaction to occur is to supply a current. And so We can hook up our cathode to the negative terminal of the battery, hook up our anode to the positive terminal of the battery. The electrons flow from our anode source to our cathode, and then from our anode in our cell back to the cathode of the battery. No different than if the electrons were flowing out of our battery to light a light bulb, and then back from the light bulb back to the other side of the battery, or through our calculator, or whatever we have our battery in. So the last topic I want to talk about is corrosion, right? Simply, when we use the generic term corrosion, really what we're meaning is undesirable redox, right? So these are spontaneous redox, or spontaneous, typically oxidations that occur that we don't want to occur, right? These are undesirable in almost all cases. That's why we call them corrosion, right? It's a negative term, right? But it is the oxidation of metal. But again, it's usually the undesired oxidation of metal. The most common example is the rusting of iron, right? Rusting is just the specific term that we use for the corrosion of iron, or the oxidation of iron. And so in rusting, our iron, right, is converted into iron ions, and oxygen from the air is reduced to form hydroxide ions, and we get our formation of FeOH2, iron hydroxide. Now, I must say, this is not actually rust. Rust is actually Fe2O3. So that initial compound that's formed, that iron hydroxide, is what initially forms. But this reaction will undergo some additional reactions to form actual rust, or iron 3 oxide, right? Which is that familiar orange flaky substance that we call rust. Now, one of the issues with rust is that it is flaky. It is crumbly, right? So it falls off the iron and exposes more iron, which leads to further rusting, which is why rusting is particularly troublesome, because it can easily eat away at these solid structures, right? It can take holes in car doors, or can degrade structural supports if left to go unchecked, or eat holes in pipes, these kinds of things. So rusting is particularly troublesome when it comes to corrosion. Now, while iron is the most well-known, lots of metals oxidize, right? You saw all those metals that were sort of higher in the table, right, are going to be subject to oxidation. They're going to be fairly reactive. Now, one of the advantages that other metals have, like aluminum and even copper, right, is the oxides that they form, the products that they form, do not flake off. They form protective coatings, in fact. So zinc also does this, right? So aluminum and copper are probably the best known, because we use a lot of aluminum and copper for like things outdoors. So we make patio furniture out of aluminum a lot of times, right? Now, if it weathers, right, a lot of times it turns like it's a white sort of coating on it, right? It turns a little, not shiny anymore. And that's because that's the oxide coating, and that's what you want, right? Because that is what protects the aluminum from further corrosion, right? Because that protective coating will seal in the rest of the aluminum. Same thing with copper, right? It gets its nice bluish, greenish color on top of it, right? It forms its protective corrosion product, right? And so it will corrode and will oxidize, but only to a point. And then it, is self-protected, if you will, right? And so a lot of other metals undergo these processes. They just don't undergo the continual corrosion because their corrosion product, their oxidation product, doesn't flake off. Now, getting back to the corrosion of iron, we have to find ways to stop it, right? We have to protect things. Otherwise, we're going to get lots of iron structures corroding over time, and we don't want that to happen, right? We use a lot of iron in construction of things like towers and pipelines that are underground, boats, ship, all of these things, these very large iron structures that we don't want rusting away. So how do we protect it, right? Well, the easiest way to protect your car or these other things is with some sort of surface protection. So for things like cars and maybe even to a certain extent ships and other things, right, this is a very manageable thing, right? We paint it, we put a protective coating, seals in the iron, and as long as that coating is in place, then we won't have any rusting occur. Right? Now, another thing that could be done is we could keep the iron dry, right? So one thing that we can mention here is that water is needed for rusting. So if there's no water, then rust can't form. Now, this is nice to say, but very hard to actually do in practice with any sort of large piece of equipment or some structural thing. So how do you keep them dry? Well, you really don't. This is practical with small iron things like iron screws and parts because you can keep them in things like oil and you can keep moisture away from them. But for large pieces, it's not really practical. Now, paint is great, but as we all know, paint chips. And we've probably all had the experience of getting a little chip in our paint and then noticing sometime later that a little rust is forming right where that chip is. And that's all it takes, right? And so we need to put on touch-up paint, or we need to repaint, or different things like that to protect that metal. Now, another way that we can protect especially larger steel structures is not with surface protection, which is really sort of impractical when you're talking about towers and large ocean liners and underground pipelines. Right? Painting is just not practical, right? The upkeep, etc. So we can use what we call electrochemical protection, right? We can actually use the activity series to our advantage here, right? So if we see where iron is on the activity series, we can pick a metal that is above iron on that activity series to, quote, protect it. So let's look at our activity series quickly. So what I want people to do is make sure they have their activity series with them. And so take a minute, you can pause the video, find your activity series, and look at where iron is on that activity series. Now, look at anything above iron. And any metal above iron can be used as what we call a sacrificial anode. So common things that are used are zinc, magnesium. Now, these are not the only things that could be used. These are just common ones that are. But because these metals are easier to oxidize, as long as you attach them, so let's say we have our iron structure here, right? We have our pipe that's made of iron. As long as we take our piece of zinc here, let's say, and we attach it by some sort of wire, something that is electrically conducting, then any kind of redox chemistry, the easier to oxidize metal is always going to be oxidized first. And so as long as this zinc is present, this iron will not undergo oxidation. So that metal that is higher in the table, more easily to oxidize, will sacrifice itself so that the iron doesn't become oxidized. And so we can do this, again, with large structures. Now, a specific application of this that some of you, I'm sure, are aware of is the process called galvanization, right? We do this often with nails and other sort of small parts that are used in outdoor construction, right? Decks and so forth. And what it does is that is coating iron with, again, zinc here. And that zinc acts twofold, right? It acts as a surface protection, but it also acts as an oxidation protection, right? Because it is attached or coating onto the iron, that zinc will be oxidized first, right? And so that prevents the underlying iron from being oxidized. And since the oxide of zinc is not crumbly, right? Once the zinc initially oxidizes, it really doesn't oxidize a whole lot more. So that zinc coating doesn't wear away really fast, right? It's pretty resistant. So you get all kinds of nice protection by simply coating your iron nails with a layer of zinc, especially when we're going to use these in outdoor construction, where they're going to be exposed to the elements. And so these are some ways that we can prevent corrosion, specifically the corrosion of iron or the rusting, through surface protection or through the use of a sacrificial electrode. So that brings our discussion of Chapter 16 to a close. So we want to go back and just, make sure you're practicing the oxidation states, understanding the activity series in a voltaic cell.